So, when we are talking about dynamical systems and their dynamical behavior, we are essentially talking about waveforms, right? And depending on whether or not the waveforms are repetitive, we say it is a periodic or aperiodic or whatever. But essentially, we are working with waveforms. And those of you who are coming from electrical, mechanical or physics or like backgrounds, you know that whenever we encounter any waveform, one of the things we always like to look at would be its spectrum. Probably you all have come across Fourier series, Fourier transform and stuff like that. So, I am not going into that specifically. So, I am assuming, I am proceeding with the assumption that you know. So, normally if you have a system with a periodic behavior, a period 1 behavior, then what would the Fourier spectrum be like? An impulse. Wait a minute. My question is that if you have a period 1 behavior, which could as well be like this, then it would not lead to just one frequency. Obviously, this is a waveform with a periodicity something like this, and if you decompose that, there will be a fundamental and there will be harmonics. But the point that I am making is that these would be line spectrum, that means very discrete spectral components, discretely spaced at the fundamental and its harmonics. Okay. So, one would expect a large, so this is the frequency axis and here is the amplitude for every frequency, say A. Then there would be a large magnitude at the fundamental frequency and there would be those smaller ones at various frequencies. Okay. One would normally expect these kind of things. For the sake of our understanding or going further, let us confine our attention to the fundamental frequency and things that happen below that. So, even though there are normally there would be these higher frequency components, we would understand that they are there, but presently let us put that out of our attention. Well, let us concentrate on this. Now, suppose as you change a parameter, the behavior becomes period 2. What change do you anticipate in the Fourier spectrum? Assuming that you recall those ideas that you learned regarding the Fourier spectrum, can you logically tell that this should happen? No. Twice the fundamental frequency, will that happen? Okay. Yes, the point is that now earlier it was the fundamental frequency was related to this time period, but now the time period will, the periodicity of the waveform will double, which will mean that a new fundamental component will appear, which is whose frequency is half. Okay. So, another component will appear whose frequency is half. Now, the way when we had this fundamental, we had those subharmonic these harmonic components. This for this one, when this is fundamental, then there would be those harmonic components also, and it is not difficult to see that one will coincide with this fellow, coincide with the already existing component that was there, and there would be the further components also. If it becomes period 4, if it becomes period 4, then obviously a new component will appear that has a frequency, that has a fundamental frequency at 1/4 the original one, right. So, here there would be and if this is the fundamental component, because of the system's nonlinearity, its harmonics will also appear, and naturally there would be components at these points. So, the overall effect of the period doubling scenario is not difficult to see, that new frequency components appearing whose periods are less than the original fundamental frequency. That is why these waveforms are also called subharmonic waveforms. The people who have been in electrical engineering, they must have heard this term subharmonic before hearing about period 2, period 3, period 4.
In period 2, so we have F naught by 2 as well as F naught.
Yes.
I mean F naught not as a harmonic, but
F, which one are you calling F naught? This one?
Period 2, first fundamental.
Yes, first fundamental. If in period 1, if that is called F naught, in period 2 another will appear which will have a frequency half the original earlier frequency. That is why this is called a subharmonic oscillation. So, let us understand them properly. You have one situation where you have one fundamental component. So, period 1. So, when it becomes period 2, then it will have this as well as this, and its harmonic will be coinciding with this one. So, this might be a little longer or so, but nevertheless there would be this. In period 4, this will remain, and there would be a new intrusion of frequency at 1/4, which will have components at half and 3/4 also, because they are the harmonics of this frequency, and there will be one component on this frequency also, so on and so forth. So, you see, as the period doubling cascade proceeds, more and more lines appear within the range between 0 and the first fundamental frequency. Now, can you anticipate what will happen as the system goes to chaos? All the intermediate frequency levels will be filled, means you will instead at this stage, let me draw the chaotic spectrum. This is period 2, this is period 4, and when it goes to chaos, you will have the whole range filled. That means you will have all the place filled. That is why chaos has the effect of spreading the spectrum. Chaos has the effect of spreading the spectrum. Earlier these were line spectra, now this would be a spread spectra. And those who are coming from electronics backgrounds, they have heard of specific applications of spread spectra, right? And in all these, chaos can be used. For example, the CDMA cell phones, they used spread spectra technology, and now there are specific propositions of using chaos generators for this purpose. So, chaos is as good as a generator of a spread spectrum waveform. So, in chaos you have a continuous frequency spectrum. Okay, this is the f axis, amplitude.
So, can we control the spreading?
Yes, it is possible, but that would be a little more tricky thing to discuss for this class. So, we will leave this out. It is not impossible to control the spreading, but that is that requires more rigorous mathematical treatment.
So, is it possible for two different systems to have the same form of chaotic motion, same form of spread?
Okay, so his question is it possible for two different systems to have the same form of chaotic motion? If by form of chaotic motion you mean the same frequency spectrum, yes, it is possible. But actually one system may be electrical system, another system may be a mechanical system. They don't, that doesn't really matter, because when you bring them to the model, if the model has same kind of parameters, they will have the same kind of behaviors, and therefore they can have the same kind of spectrum. Now, if that is the spectrum, okay, we have one more situation we had already considered, that is the orbit on a torus. Orbit on a torus. So, we considered the orbit on a torus, an orbit that goes like this. What would your anticipation be if you observe that kind of a waveform and take a Fourier spectrum? What would you get? Two frequencies, exactly two. So, if you observe it, there will be one frequency here and the frequency somewhere here. So, that is one very clear way of distinguishing a quasi-periodic waveform from a high periodic waveform or a chaotic waveform. A very clear way of distinguishing. If you simply pass it through a spectrum analyzer, you get very distinct two frequencies.
If we get a two frequencies in the waveform, is it always a quasi-periodic?
No, no. His question is, if you get two frequencies, is it always quasi-periodic? No. It is not difficult to see that if these two frequencies are commensurate, commensurate means we have learned in school, there is some number, so that these two multiplied with this number you get that number. So, if these are commensurate, that means their ratio can be expressed as a rational number. Then do you anticipate what will happen? One frequency is related to motion around a big circle, another frequency is related to the motion in the small circle. Okay, say this is f1 and this is f2. F1 is related to the motion around the big circle, and the smaller one is related to f2 is related to the motion around the small circle. Then if I ask you, will the orbit come back to the same initial condition after going around? It is not difficult to see that if they are commensurate, it will. For example, say f1 by f2 is 2 by 3. What does it physically mean? It physically means that by the time it goes around the big circle twice, it goes around the small circle thrice. So, if you start from a point, after how many? 3 rounds around the big circle, it will come back to the same position. In that case, the orbit will become periodic. So, that is also a periodic orbit, even though there are two distinct frequencies. Is that point clear now? So, even if it is a orbit on a torus, even if there are two distinct frequencies, that does not mean the orbit is quasi-periodic. It could be periodic also. So, a periodic orbit, so far we have been dealing with periodic orbit not on the surface of a torus, but now we are considering, we are also have to consider periodic orbits that lie on the surface of a torus. So, if the frequency ratio commensurate, you have periodic orbit, and incommensurate now what will happen if you have incommensurate? Actually, it will not come back to the same state. okay, the whole torus will be filled, the orbit will progressively fill the surface of the torus, it will never come back to the same state if the ratio is incommensurate, and that is called quasi periodicity. Okay. So, this is now you have learned that one way to understand these behaviors would be to place a Poincare section and see the behavior on the Poincare section. What would it be like if you place a Poincare section and see the behavior in case of commensurate frequencies? Might not be single, but a finite number of points, some number of points, but only points, because every time it starts from here and goes around it, it comes somewhere else, again after some time it will fall on the same point. So, there will be a finite number of points on the Poincare plane. If you have quasi periodic orbit, what will you see? A ring. You will see a ring, because every time it starts from here it falls in another place, again it goes, it falls in another place, again it goes and falls in another place, but ultimately none of these points will fall on each other. As a result, the whole ring will be filled. You will see a ring. It is also called a drift ring. You will see the points drifting along the ring, and it will go on doing that way. So, the signature of quasi periodic behavior is a closed loop on the Poincare section. Okay. Now, how does all that happen? Let us tackle that question at this stage. Let us come back to our concept of a continuous time dynamical system, and let us develop from there. In a continuous time dynamical system, your description was x dot is equal to f x, where x is a vector, and we are considering 3 or more than 3 dimensions, so that the period 2, period 3 chaotic motions are all possible. Suppose initially you have the parameters such that you have got one point, that is stable equilibrium point, and you have the orbit vector field like this. What would your immediate conclusion about the eigenvalues be? The eigenvalues must be complex conjugate with negative real part. Okay. And this part I have already done, just let me repeat. If suppose you change the parameter, vary the parameter, and as a result of that the eigenvalues move across the imaginary axis to the positive side, what will happen? In the immediate neighborhood of it, it will become repelling. But that does not mean that away from it, it will still be repelling. So, away from it, it could be attracting, and as a result there would be a limit cycle. So, this is the birth of the limit cycle that we discussed. This phenomenon is normally called Hopf bifurcation. This is obviously a bifurcation because the asymptotic character of the orbit changed. There is a fundamental change in the character of the orbit, so it is a bifurcation. It is called Hopf bifurcation. So, Hopf bifurcation is actually related to where in the complex plane the eigenvalues actually move like this. This is the real axis, this is the imaginary axis, and the eigenvalues move like this. At this point we have the occurrence of the Hopf bifurcation. So, we have the birth of the periodic orbit, and thereafter when we tried to study the stability of it, what did we do? We placed a Poincare section, and that is how we did it. So, thereafter we found it more convenient to study it in discrete time. So, we said that let us place a Poincare section, and now let us study the stability of this. That is how we proceeded. Okay. And then we said that okay, now we can locally linearize around that fixed point of the map if the eigenvalues are less than unity in magnitude, then you have a periodic orbit, this fellow is stable, and so on and so forth. So, we were considering the situation where we have the eigenvalues inside the unit circle, and we have already done that. I am not repeating that. The point is, if the eigenvalues of that fixed point, eigenvalues of this fixed point of the map, not the continuous time dynamical system, of the map at the fixed point are complex conjugate, and say they are stationed somewhere like this. So, this is the real axis and this is the imaginary axis. What would the behavior be in discrete time? In discrete time, I have done that. Suppose this is the fixed point, then the behavior would be a spiral. It should go through discrete jumps, but then it would progressively the distance between the points will reduce, and the vector will rotate. The rotation will be given by the tan inverse b by a term, okay, and the shrinking will be given by the magnitude of the eigenvalue. So, essentially we get a incoming spiral. If say they move like this, what will happen? It will become outgoing spiral. So, again a similar situation is unfolding, but in discrete time. So, initially it was a incoming spiral behavior. I am drawing continuous line, but it is not continuous really, it is discrete jumps. It was like this, and then it became like this. Again we can raise the same issue, that outside, away from this fixed point, you cannot guarantee that it is still outgoing. So, there can still be incoming directions, as a result of which there will be a, in this case we will not call it a limit cycle, because now it is happening in discrete time. Now it is happening in discrete time. So, we will not call it a limit cycle, rather we will say that now what has happened is that we have seen the birth of a closed loop in discrete time. A closed loop in discrete time means what in continuous time? A torus in continuous time. A closed loop in discrete time, whenever there is a birth of a closed loop in discrete time, you immediately know that there is a torus in continuous time. So, this is how a torus is born in a continuous time dynamical system. So, when we try to understand that, we try to understand that in terms of the discrete time behavior, in terms of the birth of a loop, birth of a closed loop. But now, this closed loop has been born. Quite a natural question is that this closed loop has obviously two frequencies, and I said depending on the frequencies and their ratio, it is either a periodic orbit or a quasi periodic orbit. But physically, how can two frequencies be there physically in a system? Well, to get a physical idea, you might imagine it this way. One, suppose the system has some kind of a LCR circuit, a LCR circuit means there would be some characteristic frequency, and supposing it is excited by a sinusoid which has a different frequency. So, obviously, there are two characteristic frequencies in the system and they will interact with each other. Okay. It might also be so that there is no external periodic input, but there are two parts of the system which have their own LCR circuits, or maybe a electrical component which has its own characteristic time constant, and there is a mechanical part which has its own characteristic time constant, because there are springs, masses, friction elements which are similar to LCR. So, there are two characteristic frequencies, and as the dynamics unfolds, there will be interaction between these two characteristic frequencies. Okay. There will be interaction between these two, and that is what gives rise to this kind of behavior. Okay. So, normally you would expect quasi periodicity to occur in systems which, if you look at the system description, you should be able to identify what creates the frequencies normally. But there are also situations where it may be, it may require a lot of insight to find out what exactly is creating the frequency, but nevertheless there should be that kind of a situation. You have already done in mathematics course or in other courses, supposing there is a simple LCR circuit, a linear system excited by a external harmonic sinusoidal excitation. What will be the behavior like? Sinusoid, right? It will be a sinusoidal behavior.
It will be one frequency and the excitation frequency.
Yes, it will be the excitation frequency only. So, in case of a linear system, the effect of the original system's time characteristic time is not all that visible. But if the system is non-linear, that is not quite so. Then there is interaction. You might imagine that, supposing
Instead of saying it's a linear system, that's why we get only the excitation frequency. But if we have any non-linear component with it, then we can get both.
then we can have more complicated behavior. That's all that I am meaning at the moment. In such systems, you would anticipate the possibility that when you have only the excitation frequency visible, then it is a periodic orbit. In the state space, it is a closed loop. Take the Poincare section, it is a point. But then, because of the non-linearity, as you change the parameters, there might be a situation where this closed loop might become unstable, and as a result, a additional loop may develop on the Poincare plane. Is that clear? It is possible then. But then there is something more to it. What is more? What is more is this, that okay, supposing there is a frequency f1 and there is another frequency f2, and as I said, if this ratio is commensurate, then you have the periodic orbit. If that is incommensurate, you have the aperiodic orbit. Now, supposing I keep f2 fixed and I vary f1, I can do that. What would the anticipation be? That in order to get a periodic orbit, you have to actually fix f1 with infinite precision, right? Because if you slightly vary, you will get a irrational number. Or if you want to obtain a quasi-periodic orbit, you have to really fix it at a irrational number very accurately, because around a irrational number there is always some rational number. Okay? That is a fundamental theorem in number theory. Got it? So, the natural anticipation would be that in order to get any desired behavior, you need to fix the frequencies very, very accurately. No. No, because of the non-linearity. What happens is that if you keep f2 constant and vary f1, or keep f1 constant and vary f2, you will find that mysteriously the two frequencies get locked for some range of the parameter. Get locked means they get locked into a particular ratio, that is it, for a long ratio. As you change the parameter, it does not get away very easily, and then at some particular parameter value the locking is lost, and then you have again quasi periodic behavior, again it gets locked to some other frequency. This is called mode locking or frequency locking. Very interesting phenomenon and completely nonlinear phenomenon. It cannot happen in a linear system. This mode locking is a very interesting nonlinear phenomenon. So, this is called mode locking or also frequency locking. So, let me just repeat, if you keep on changing the parameter, you normally anticipate that you have to fix the parameter very accurately in order to get a rational frequency ratio, but it is not so. Mysteriously you will find that for a large parameter range, for a range of parameters, the same ratio remains fixed. That means they get locked.
So, if you change it, lock can be broken.
Yeah. If you change it beyond a certain range, the locking may get broken.
In electrical system, can there be two locking frequencies? I mean, F1, F2 and F3, F4.
Wait. No. Presently we are talking about only two frequencies existing. I will come to those issues a little later. How does this happen? How does this physically happen? Well, if you want to imagine how it physically happens, I can give you a sort of hand waving argument. See, if you have one frequency somewhere here and if you have another frequency somewhere here, and then these two are in a rational ratio, then there should be some kind of a harmonic somewhere here, harmonic of this one, and there should be another harmonic of this one whose frequencies will match, as a result of which there should be a resonance between the two. That resonance cannot happen if the frequency ratio is incommensurate. So, if the frequency ratio becomes commensurate, then there must be some particular frequency out there in the higher frequency range where both the components will have some harmonics there. There should be a resonance, and the resonance itself is a nonlinear phenomenon. That resonance sort of holds on, it does not let it go very easily. So, only when this is moved by significant amount does this move away, otherwise the resonance sort of locks hands and remains there. Okay. So, that is the intuitive way of seeing how it happens, intuitive way, sort of electrical way of seeing how it happens.
But who will maintain the resonance?
The system's nonlinearity. The system has to be nonlinear in order to have any resonance. Here we are talking about nonlinear system. The system's behavior has to have some kind of a nonlinearity built into it, and that produces the force. One side, because of the nonlinearity, must apply a force on the other frequency so that it gets locked. That is happening because
in LCR the characteristic is omega naught. There we get a resonance in LCR.
No, wait. I am not talking about the linear system's resonance. There it happens only if you have excite at that particular frequency. Here we are saying that no, we are not exciting at that particular frequency, we are moving it, yet it is getting locked. So, that is a nonlinear phenomenon, cannot happen unless there is a nonlinearity in the system. But examples of such situations galore. For example, you know that there are at least two, even more actually, but two very well known situations within the solar system where it has happened. The Earth Moon system. You know that you see only one side of the moon, right? You do not see the other side of the moon. Why? The moon is rotating around you. So, if Earth is rotating around yourself, Earth is rotating around its own axis and the moon is rotating around Earth, then obviously I should see all sides of the moon because moon is rotating. We don't see. What does it mean? It is actually in the phase space, it is a motion on a torus with ratio 1:1, and it is a mode locked behavior. There is no guarantee that it was always mode locked. It might be at the time of dinosaurs it got mode locked, so that if the dinosaurs could see, they could have seen the opposite side of the moon, but at that time maybe it got locked. But there is no guarantee that it was always mode locked. It got mode locked at some point of time, and we are in a temporal phase where it is still mode locked. Mercury, for example, same phase faces the sun, and in that particular phase the temperature goes to something like 600 degrees. In the other side it is freezing, minus how much? In Mercury, the closest thing to the sun. The other side, that is in the shade, is its freezing temperature. Because of that, because there is only one side that is exposed to the sun. These are mode locked behaviors, and such mode locked behaviors are very common in experimental engineering situations also. So the total picture is that if you start from a initial condition, say if you look at the bifurcation diagram, suppose I am doing the wrong way of plotting the bifurcation diagram. That means I am talking about a birth of a equilibrium, and that equilibrium, say I am changing the parameter, and here is some kind of variable that I am plotting, and at that point of time that equilibrium started to exist, not the fixed point. Remember, I am talking about the equilibrium point in the continuous time system. At that point a Hopf bifurcation occurred, as a result of which what was born? A limit cycle. A limit cycle, if I now draw, then I can only draw the projection on the x component. So what we will see, its value will slowly increase, so like this. Right. So I am talking about this orbit, this orbit, this orbit. So these are all orbits like this. And suppose at some point of time that again loses stability, that periodic orbit loses stability, as a result of which what is born? A quasi periodic orbit. So then that would be signified by some kind of a change. I am not depicting because it is difficult to depict that. Then within that range where it is a motion on a torus, as you are changing the parameter, there would be a succession of mode locked behaviors, sandwiched between them would be quasi periodic behaviors. Mode locked, quasi periodicity, mode locked, quasi periodicity. So you would see that there would be some range where you have quasi periodicity behavior, and some range where you have some kind of a mode locked behavior, again a mode locked behavior, again a quasi periodic behavior, again a mode locked behavior. These are not chaos though I am drawing this way because all the points on the loop would be filled in quasi periodicity, but again there would be some mode locked behavior, again a quasi periodic behavior. So the behavior would be something like this, and finally at some stage that gives rise to chaos. So here there would be a range where it gives rise to chaos. The torus breaks down. This is called the quasi periodicity route to chaos. We have already learnt about a few routes to chaos. We have learnt about the period doubling route to chaos and things like that. This is the quasi periodicity route to chaos. It has actually history. The history is that you must have heard of the names of the famous Russian physicists Landau and Lifshitz, the famous book, almost the Bible in physics. This man Lev Landau in early 40s, he proposed a mechanism for generating turbulence. Turbulence means a chaotic behavior. Now we understand that as a chaotic behavior, but how is it produced? His point was that as you change the parameters, for example, in case of producing turbulence, you increase the flow rate, and beyond a certain flow rate you find turbulence. So, increasing the flow rate, that is the parameter. Suppose you are increasing the parameter, changing the parameter, then he says that beyond a certain parameter another frequency component comes in. Beyond another parameter, if another frequency component comes in, another parameter, another frequency component comes in. So, his proposition was that there is a progression of addition of frequency components. Finally, there is a situation where all the frequency components are there, and that is turbulence. Is that clear? It is almost the same kind of situation as period doubling cascade. His proposition was that it is a accumulation of frequency components that finally gives rise to a chaotic behavior. That proposition, that sort of it was I should say a conjecture, finally proved to be wrong. That conjecture finally proved to be wrong. Now we understand that the first transition, that means while from the laminar flow, the first transition, accumulation of one frequency component is possible, another frequency component is possible. You can see that addition of one frequency component is the first bifurcation, Hopf bifurcation, creating a limit cycle. Second one is the second one happening on the Poincare section, creating a closed loop, that is also addition of frequency component. But thereafter we have a problem. When you have a periodic orbit, it is a one frequency behavior. A torus, a two frequency behavior. Naturally, the question is, can there be a three frequency torus? The mathematical question boils down to that. Okay. People who were doing experiments, they found that they are somehow not finding it. They are somehow, in all experiments, they are finding that after the two frequency torus, it somehow goes directly into chaos. Somehow. Then, when I say these experiments, I am talking about the time frames like 80s. So, there was a very long span of time when people believed that the Landau mechanism is true, but people found that we are not getting it. In the 80s, some people did experiments very carefully on oscillators, where they carefully created one characteristic frequency of one part of the oscillator, another oscillator with another characteristic frequency, and a third frequency, that is a injection frequency. So, deliberately created a situation where there will be three frequencies. They found that if the interaction between the two, that means coupling between the two oscillators, is weak, then you do get three frequency behavior. But if the coupling is strong, then the two frequency behavior directly goes into chaotic behavior. But we have never found anything beyond three frequency behavior. Three frequency torus I will not be able to draw, because it is a conceptual thing, you cannot draw it on the sheet, it is not possible to draw. But essentially the concept is there should be, if you break up in frequency spectrum, you see three frequency components. Then came the theoretical breakthrough, where it was proved that the three frequency torus behavior is structurally unstable, in the sense that if you slightly perturb that three frequency torus, slightly perturb means either you change the parameter or you change the initial condition or whatever, slightly perturb it, it goes into a chaotic behavior. So, even though theoretically a three frequency behavior is possible, that is why it is extremely difficult to observe, because it is structurally unstable. Is that point clear? The mathematical statement says that in the neighborhood of every three frequency torus, there lies a strange attractor at an infinitesimally small distance. okay, which essentially in physical terms means that even slight bit of random noise existing in any system will not allow it to stabilize in the 3 frequency behavior. Okay. And that is why you do not see the progression from into 3 frequency, 4 frequency, 5 frequency and all that going into chaotic behavior. So, now we understand that the essential mechanism of this quasi periodicity route to chaos is where you have a periodic behavior, period 1 behavior, then a bifurcation leading to a torus behavior, and that torus somehow breaks down. There is some mechanism by which the torus itself breaks down, and that leads to chaos. How can the torus break down? Well, torus is a very well defined geometrical structure. For mathematician, for a topologist, the torus is a very well defined concept. Like if it is a torus, if it is a donut, you can take a thread through. So, if it is a torus, then you can take a thread like this. If you take like this, then you cannot take it out without breaking the torus and stuff like that. There are very well defined mathematical concepts by which a torus is defined. If that somehow breaks down, that means some deformities appear in the torus, so that it can no longer be called a mathematical torus. That is a transition from a torus behavior to a chaotic behavior. That is another route to chaos. Before concluding today, let me give you a name. We said that there are 2 bifurcations appearing on this. One at this point. What happened on this point? What is the name? Hopf bifurcation. What happened at this point? It is the similar thing to Hopf bifurcation happening in discrete time, right? That is why some authors call it also Hopf bifurcation. That means, this is also called a Hopf bifurcation. In some books you will find that this is also called a Hopf bifurcation, but more accurately this bifurcation, so this is called a Hopf, and this bifurcation is either called a Hopf or discrete Hopf or generalized Hopf, or there is another name for it by the names of the people who actually discovered this mechanism. It is also called the Neymark-Sarkar bifurcation. So, what is the characteristic of the Neymark-Sarkar bifurcation? In the discrete time, you have got a fixed point, you locate the Jacobian, locate the eigenvalues, and the eigenvalues would be complex conjugate and exactly equal to 1 in magnitude, then it is a Neymark-Sarkar bifurcation. Okay. So, do not be confused by these 2 interchanging names in different literature. Same phenomenon, conceptually, since it is the same as the Hopf bifurcation in discrete time, it is also called Hopf or generalized Hopf and Neymark-Sarkar. How much time do you have? Okay, let us explore the issue of the mode locking a little further. Suppose you have 2 frequencies f1 and f2, their ratio is commensurate, and say that commensurate ratio is p by q, where p and q are whole numbers. P and q are whole numbers. So, f1 by f2 can be expressed as p by q. Remember, when I say p by q, I am not saying something like okay, 10 by 6 is equal to 2 by 3, and then I would write 2 by 3. So, whenever I say p by q, in the further discussion, you assume you understand that all the common divisors are taken out. So 2 by 3. What does 2 by 3 mean? 2 by 3 means by the time it goes 3 circles around the big, it goes twice around the opposite. By the time it goes twice around the big circle, it goes thrice around the small circle. So what does it mean? On the Poincare plane, what will you see? Suppose this is the Poincare plane. There is a closed loop on the Poincare plane. Okay. There is a closed loop on the Poincare plane, and suppose I start from this point. So after this, what will happen? It will go into the big circle, and after some time it will come back on this. Where will it come back? 2/3 of the circle later, right? If the ratio is 2 by 3, so it will come back here. So if this is point number 1, this will be the point number 2. Where will it intersect the Poincare section again? Again 2/3 of the circle later, here. Again, so this point returns as the 4th point, right? So this is what we will see on the Poincare plane. Clear? A 2 by 3 behavior, f1 by f2 is 2 by 3, is actually seen as this. What about a, say, 3 by 5 behavior? Can you draw? f1 by f2 is 3 by 5. Three by 5. So in that case, suppose you start from here. Oh, I should actually call it 0 because it is a starting point. So this is 0, 1, 2, and this is 3. Here it is 0. Then after that, it will go into the big circle and it will come back on this Poincare plane after how much angle? 3 by 5. 3/5 of the circle. 3/5 of the circle, say it is somewhere here. That is point number 1. Okay. Point number 2 is again 3/5 of the circle, say somewhere here. 2. Again 3/5 of the circle, somewhere here. 3. Again 3/5 of the circle, somewhere here. 4. Again 3/5 again. Is that clear? So even though things are happening going out that way, we are being able to see things simply by looking at the Poincare plane, and we are being able to conclude about the frequencies. Notice what I am meaning. Meaning that the torus is there. Suppose I am not looking at the torus, I am only looking at the section. Therefore, you tend to believe that the other frequency will now go out of my attention. This orbit will no longer be seen because I am seeing only this. No, it is still visible to us because the way it rotates. The way it rotates, that tells us how it goes into the big circle. Clear? Okay. We will develop on this idea further in the next class. Thank you for today.